Good day, everyone, and welcome to where we are putting together solutions for students who are getting problems in the area of mathematics, and specifically in this channel with regards to primary math. We'll be looking in this video at the secondary entrance assessment, and we're looking at the past paper questions for SEA 2020, specifically section 1. Section 1 consists of all 20 questions with 1 mark each. Don't forget to like the video and add any comments down below so we can help create other videos for you in whichever areas that you are struggling with. We also have channels at the CSEC math level, the Form 5 level for students who are struggling from 2009 until the present in terms of topics, so that students can study specifically there, and the same at the additional mathematics levels as well. All these can be found in the description down below, links to the other channels, and also the playlist to how you should study for this secondary entrance assessment. We now look at the distribution of questions in section 1 with these 20 questions. The first one was based on number, and number takes up half of the questions in section 1, 10 questions. And let's recall that the syllabus is split up into 4 parts or 4 strands in mathematics, and the second strand will be measurement, and that is tested for the next 4 questions from 11 to 14. And then the third strand is geometry, which will be tested from 15 to 17, the next 3 questions. And finally, the last strand is statistics, and those will be tested for the last 3 questions in this paper in section 1 from 18 to 20. Number 1, complete the place value chart to represent the numeral 45,306. And if we look at this question, we can see that the value of thousands was already given. So there are a couple of ways to do this. Some of you can easily tell the answer, which is 45,306. And just for a little clarification, let's recall that when we are thinking about this number here, the first value, the 6, is a place value ones, and then tens, and then hundreds, just as shown above. And what happens next? This pattern is repeated. So the fourth place value would be ones, and then tens, and it can continue hundreds, and the pattern is repeated again and again, right? Where these 3 values are repeated. So the first set, ones, tens, and hundreds, actually deal with ones, and then the next set will be dealing with thousands. And if we're going to another set of ones, tens, and hundreds, it will be going on to millions. So this indicates that the 4 tens and 5 ones means 45,000, and of course 306. Number 2, write a whole number in the box to make the statement true. So if we look at our statement that was given, it is saying 3,100 plus something, and it's giving us an inequality sign, will be 3,124. So let's recap 2 things. First of all, what is a whole number? And if we consider whole numbers, we can bring it up using a number line where we're seeing that it starts at the number 0, and then it continues 1, 2, 3, 4, 5, and so on and so forth. Those are our whole numbers. So the question is asking us to write a whole number in that box so that the statement is true. Now let's look at this statement again. Look at that inequality sign before the 3,124. And if we bring it up, and let's sort of expand it a little bit, sort of looks like an L. And if we consider putting our two hands flat on the page in front of us, and we can look at our hands there, we can see one of those hands forms an L. And that is our left hand. And similarly, let's think of it mathematically. Let's do the same shape again and rotate it. So L is for left hand and L is for less than. So this here indicates that the question is stating 3,100 plus some number, which is a whole number, is less than 3,124. So let's bring that up on the number line. We can see 3,100 and 3,124. So we need to figure out what whole number fits in between there to connect one to the other, where one side is less than the other. So we can rewrite it. 3,100 plus the whole number is less than 3,124. And of course, we can see on the number line, it means that on the left-hand side, we would want our answer to be at least 3,100. That is the smallest whole number, which is 0. Or if we add a bigger number, it can increase and keep increasing up to 3,124. But the question is, does it include that? If our total on the left-hand side works out to be 3,124, then it is not less than the right-hand side. So we cannot include that number 3,124 in the number line. So we draw a circle where the inside is empty. While we were able to include what it was at 3,100 on the left-hand side, so we shaded that. So let's go work it. We can take away 3,100 from both sides. So that means that our whole number, which is the box, will be less than 3,124 minus 3,100. So the green lines that we had with the two circles on them, the closed and open circles, indicates the same thing. And of course, we can work that out. So 3,124 take away 3,000 is 24. So it tells us that the whole number that we're interested in must be less than 24. So if we look at our whole number here and we rearrange a little bit, so we can see 0 and 24. It means our whole number must be less than 24. So we can slide this across, indicating where our whole number lies in order for this statement to be true. So if we bring up our answer, what are the possible answers? Can 0 be an answer? Well, if we put it into our original statement, 3,100 plus 0 is 3,100, and that is less than 3,124. If we go along this line up to 12, 3,100 plus 12, it's still less than the right-hand side, so it works. So any number from 0, 1, 2, 3 up to 12 works. Let's continue. What about 13? 3,100 plus 13 will also be less than the right-hand side. 3,100 plus 23 will give us 3,123, which is also less than the right-hand side. So all of those works. What about if we put 24 as the whole number? If we say 3,100 plus 24, does it give us something which is less than the right-hand side? Actually, it does not. It gives us something that's equal. So our possible answers, and there are many answers that can work out or that can be substituted into the box for the statement to be true, will be any number from 0 to 23. Any one of the numbers that you put there, 0, 1, 2, 3, straight up to 23, will make the statement true. Let's go on now to number 3. What number is represented by 3 times 100 plus 7 times 1 plus 5 times 1/10? And of course, some students can easily write it. And we just want to recap how it works. If we think about bringing up the place value, and we start at ones, and many of our teachers use this system using a base 10 block or the Dean's blocks to explain it in class. So we can use that and said, well, okay, look, we have a rectangle, and we're going to say that the rectangle represents ones. And if we have a tall rectangle, 1 by 10, representing ones, then how do we represent tens? We want 10 sets of those. So 10 sets of those will give us 10 by 10, which is a square. And if we want to get hundreds, then it's 10 sets of tens. So it will look like this. So we've used this before many times in class, right? So just a little reminder. So now let's go and look at the number that we're looking for, 3 times 100 and so forth. Now remember that we want to get something which is 1/10, something which is smaller than ones. So how do we do that? We bring up a decimal point. That indicates that if we're going to the right, we're getting 10 times smaller and something smaller than ones. So if that rectangle there, it's long and it had 10 little parts in it, and we cut it into tens, then one of these will represent something smaller than ones, 1/10 of it. So we can bring up our decimal point to show the place value up on top as being tenths. So this may be a little shift from what we're accustomed to, where we start with the one single small cube as being ones and so forth, but we can shift it forward or backward according to where we want to represent. So now, what number is represented? We have 3 sets of hundreds, so you can put 3 of these, and we have no tens, but we also have ones. And how many ones do we have? We have 7 ones. So 3 and 3, 6 and 1. 7 ones represents it. And then we're getting smaller than ones. So we put a decimal point. And how many of those? It will be 5 of them. So hopefully we can see the representation of it. And now what does that mean? We have 3 hundreds. How many tens do we have? We have no tens. So we put a 0 to represent that. And how many ones we have? We have 7 ones. And of course, we're getting smaller, so we put a decimal point. And then we have 5 tenths, or half. So our answer can be written as 307.5, or 307 and 5 tenths, or 307 and a half. Let's now go on. The total value of the 5 bills shown below is $81. Write the missing value on the bill. So there are many different ways to do this, and I know in every SEA class, teachers have a number chart stuck up from 1 to 100, and students use it regularly because they're so familiar with manipulating numbers within there. So let's do the same thing. So let's consider the first number, right? Remember, we want to end up at 81. That's our goal. So our first bill is $50. So we can represent that. We have it in green as 10, 20, 30, 40, 50. So we can see that represents the bills. And what comes next? We have a $20 bill. So what comes after 50? We have it in yellow, so we represent it by 10 and 10, 20, same color. So what it tells us is $50 plus $20 is $70. And we have some more. We have $5 represented as purple. So we can represent that. 70 will go to 75. And we have $1 bill, which carries us to 76. So we're almost there. Now, how do we reach 81? There are a couple of ways to do it. One way is to count forward. So from 76, we're counting 1, 2, 3, 4. That carries us to 80. And we want to go one more to 81. So that means we've counted forward 5 jumps or 5 ones. So the bill that is missing is a $5 bill. Another way that teachers normally represent it is ask the students to go and add up everything. So we have $50 and we have what next? $20. one in green, one in yellow, and then we had what is in purple, $5, and of course $1. So we can go and add this up. So if we add the ones columns, we're going to get 0 and 0 and 5 and 1 is 6. And we add the tens column, that will give us 76. And if you looked at our 100 chart, it did the same thing. It added 50 and 20 is 70 and 5 is 75 and 1 is 76. And since teachers normally use one of these two methods, let's continue here. We have $81, that's where we want to end up. Let's represent $81 for us so we can easily see that. We always want to be able to connect our numbers to something physical. So it's easier for students to represent that. Now we have $81 and we would like to take away 76 to see how much we need again. How do we do that? Well, we work on the ones and we see we have $1 minus $6. Can that happen? Can we take 6 from 1? No, we can't. So what do? We will have to do a little manipulation. So instead of having 8 of those tens, we can now remove it to have 7. So what does that give us? By taking out one of those tens, we can replace it by 10 ones. 5 and 5, 10. So that is considered to be regrouping or carrying, according to what your teacher says. So we had 8 tens and we needed to get 1. So some teachers make you write 7 and then a 1 alone, 1 by 1 will give us 11. I prefer this way, that the one of the tens was replaced by 10 ones. So we have 10 and 1, 11 ones. We see it on the right hand side. And now we're going to subtract 6. So of course that means 5 and 1, 6. We start with a bigger number, easier to count. So that tells us that we have 5. And now in the tens column, we have 7 tens, and we need to subtract 7 tens. So that removes all, so our answer is left with 5. So this is a different way to show the same format. Let's go to number 5. Paul picked 1,725 mangoes. Estimate the number of mangoes he picked to the nearest 1,000. So if we consider a number line and we're counting in thousands, just as they asked us to estimate, we have 0,000, 1,000, 2,000, and so forth. And we're looking at the number 1,725. So that means if we put values on them, you'll see the place values as 0, tens, hundreds, and thousands. And how many thousands do we have? We have either 1,000 or it will go up to 2,000, somewhere around there. So we need to figure out which one will be our answer. And since we have 2 of those, we can put a benchmark, meaning we can find the middle of it. And if we do that, what's the middle of 1,000 and 2,000? 1,500. So using that as our benchmark or as our guide, we know that if we were at 1,500, we would have the same distance to the left to reach 1,000 as to the right to reach 2,000. But look at our number. Let's go back to the question. Paul picked 1,725 mangoes. So will that be on the purple line, on the left of the line, or on the right of the line? 1,725 falls to the right. And we just give an average so students can see what's happening. So what does that mean? If we're estimating it, we're trying to find where is it closer to. We can see that the black curly brackets represent the distance, how far away it is from 1,000, and the red one represents how far away it is from 2,000. So the question is asking us estimate the number of mangoes he picked to the nearest 1,000. So which is the nearest 1,000? Is it the one that we're using with the black curly brackets or the red curly brackets? We can see if it's closer, it's the red curly brackets. So our answer is 2,000 mangoes. Number 6. Jamal baked the cookies shown on the tray below. He ate 2/15 of the cookies. How many cookies did he eat? So if we look at the tree, we can count them and we see if we're coming downwards 1, 2, 3, 4, 5 cookies, and another column of 5 cookies, that's 10, and another one 15, 20, 25, 30. So there are 6 in each row, and there are 5 rows. So 5 sixes are 30 cookies. And there are a couple different ways to do this. One of the ways we can look at identifying it by splitting up the tree, going across horizontally. So let's do that. So we'll have one path, 2, 3, 4, 5. So we've split it up horizontally, going across into 5 parts. So each of these parts has 6 cookies, and each of these parts is 1/5 of the tree because there are 5 parts to make the entire tree. Now we don't want it in fifths, we want it in a greater denominator, which is 15. So we want to split it coming downwards. If we split it in the middle, let's bring up a red line. Then one line down means that we've split it on the left and right. So we have 5 and 5, 10 parts. So that means that each one of those parts is 1/10. Let's look at the question again. He ate 2/15, not 2/10, but 2/15. So we don't want it in terms of tenths, but we want it in terms of 15s. So let's remove that line and let's consider breaking it up into 2 lines coming down. So that will give us vertically 1, 2, 3 columns. So we have 5 threes are 15 parts. So now we can identify one part. So 1/15 of the tree will tell us how many cookies did he eat. He ate 2 cookies. But if we look at the question, he ate 2/15 of the tree. So that means 2 of those parts. So 2/15 of the tree would be 2 plus 2 is 4 cookies. As such, our answer, how many cookies did he eat, was 4 cookies. Another way teachers ask students to do it would be to just go and do the multiplication. So 2/15 of 30. And we got 30 because there are 30 cookies in all, 6 fives are 30. And now, is there anything that can cancel or break down or reduce? Well, 15 and 30, do they belong to the same tables? Yes, they do. They belong to the same tables that you know that your teacher does with you regularly. If we consider a clock, then at quarter past, that's 1 quarter turn, it's 15 minutes, and 2 quarter turns is 30 minutes, which is a half. So therefore, if we go 15 into 15, that will give us 1. And how many 15s or quarter turns will give us 30? That means 2 of them. So 2 times 2 is 4 cookies. Let's now go on to the next question, which is number 7. We're still on the number strand, or that part of the curriculum. Ariana spent 2/3 of her allowance and had $10 remaining. So we could bring up a diagram. Let's bring up a circle, and we want to split it into 3 parts because we are talking about thirds. Right? She spent 2/3. So we take the circle and we just could make a little sketch and split it up. And what we know she spent 2/3, 2 parts. So we'll put that as spent and had $10 remaining. So the remainder is $10. What's the question? How much was her allowance? So her allowance was everything. And there are a couple of different ways we can do this. As usual, in mathematics, there are many, many different ways to solve any single question. So, one way to do it is recognizing that 1 out of those 3 parts is $10. So, if we look at the blue ones, which was spent, then there's $10 for the first part and $10 for the second part. So, now that we know that, what does the question ask us? How much was her allowance? The answer is $30. 10 plus 10 plus 10. Another way to do it, we can consider 1/3 of our allowance is $10. Right? Some teachers prefer that you draw the diagram and do it, which I prefer as well, because students are now able to see and understand the problem. Some prefer the method down below. 1/3 of our allowance is $10. So if we want to find the whole thing, that is 3/3. 3/3 is a whole. So it'll be 10 times 3, which is $30. And of course, I've found that students who are getting problems with math need to see some sort of visual, some sort of model or representation. So we can draw a circle to do it, or we could have even used a different shape. We could have used a rectangle and just split it into 3 parts. Simple enough. Freehand, take 10 seconds to draw, and of course, represent it where we see what is spent and what is the remainder, and go about and do the same solution. We now move on to the next question, which is number 8. 6 minus 4/7, and this is with 1 mark. And there are a couple different ways to do it. So if we consider that we're looking at fractions whose denominator is 7, it means that if we have a whole, then we can break it up into 7 parts. 1, 2, 3, 4, 5, 6, 7. And how many wholes are we starting with? 6 of them. So we have one whole at 7 parts, a second one at 7, a third one, a fourth one, a fifth one at 7, and 6 sevens. So we actually have 42 of those small parts, or 42 sevens, minus, and what we're going to take away, 4 of those parts, 4 sevens. So some teachers prefer you say 42 sevens minus 4 sevens and give us 38 sevens, and then go convert it into a mixed number. Or some will say, well, simply, if we take a look at this, how many wholes are there? There are 5 wholes, we have in green, and 3 parts, 3 sevens. So simply the answer is 5 and 3 sevens. We could have done it drawing circles as well, but some students prefer to draw the rectangle. The circles are a little difficult to split into 7. Other ways that teachers prefer, instead of taking 6 as 6 wholes, they can break it up into 5 plus 1, that's 6, minus 4 sevens. And now we actually know we have 5 is going to be in the answer, and we just have to work out 1 minus 4 sevens. And you can see from the diagram, we already have the 5 wholes, and in the 6th hole, where that's the 1, then we just take away 4 sevens from it, and we're going to get 3 sevens. Some people prefer that we try to use the idea of doing some sort of equivalent fractions, right? Well, let's recall from this normal column we see stuck up in our classroom, where this is our multiplication tables. Many classrooms have been in. We see that. Then what's the first line? Let's look at the 1 times table. 1, 1 is 1, 1, 2 is 2, 1, 3 is 3, 1, 4 is 4, and so forth. We know that. And if we consider the whole 1, 1 is really 1 over 1. And 1 over 1 is the same as 2 over 2, or 3 over 3, or 4 over 4. And in this case, we're dealing with sevens. So it's the same as 7 over 7. So we can replace that 1. So we have 5 plus 7 sevens minus 4 sevens. So and that is the same diagram down below. On the right hand side, you can see it. 7 sevens is the 6th one. And we're subtracting 4 sevens. And of course, that will give us our answer. 5 and 3 sevens. So we're seeing a couple different ways to work this question. We can also look at the idea where teachers teach it using a number line. And there are benefits to each one of these. And it's good for students to be able to recognize different ways of approaching the question. So we're looking at 6 minus 4 sevens. So if we look at that there, then it will really be focusing on this little area of the number line. And I'll extend it a little bit so you can see it properly. And if we have this, that is really dealing from 5 to 6, we want to break it up into sevens. So just as we looked at the rectangles up on top, in order to break up a whole into 7 parts, we need to draw 6 lines. Then let's do the same thing. 1 line, 2 lines, 3, 4, 5, 6. And if we put the numbers on, we started at 5, 5 and 1 seventh, 5 and 2 sevenths, 5 and 3 sevenths, 4 sevenths, 5 sevenths, 6 sevenths, and 7 sevenths. And of course, 5 and 7 sevenths is 5 and a whole, which is 6. So this is a different way of representing it. And look at the question again. We're starting with 6. So let's put a little marker here. And we're subtracting 4 sevenths. So it means we're going to the left, 1 seventh. We're jumping across 2 sevenths. Some teachers use a frog to jump in class. That's fine. So we move 1, 2, 3, 4. So that's 4 sevenths across. So what is our final answer? 5 and 3 sevenths. Okay, let's move on to the next question. Number 9, which says, write the correct value in the box to complete the number sentence. So if you look at the number sentence, it's saying 16 times 11, or 16 sets of 11, or 16 groups, is equal to 4 groups of 11, and how many groups of 11? And some students can watch this and immediately say, well, the answer is 12. If I have 16 groups, I can split it up into 4 groups and 12 groups, because all the groups are groups of 11, or sets of 11, or multiplying by 11. I would prefer that students also think about it as recognizing that when teachers are teaching area, it's the same question. 16 times 11 is actually a large rectangle, 16 across, 11 up, and we can break that up into 2 parts. First rectangle, we already know it's 11, and we can say the bottom is 4, so 4 times 11. So we had an entire rectangle 16 by 11. That can be broken up into 2 parts. One is 4 by 11, and the second part. And the second rectangle, that second part, we know on the right-hand side, it will be the same as the left-hand side, it's 11. So how many 11s? If the whole width across is 16, and one part is 4, that means the remainder is 16 minus 4, which is 12. So that tells us that we have 12 sets of 11. Teachers do it this way as well because they want to remind us that 2 times 8, let's use smaller numbers. Sometimes when you're in the question and you get in difficulty, you use smaller values and work it out so you can pick it up easily and then follow the pattern. So 2 times 8 will look something like 16 times 11. And we can break up the 8. So we get 2 times 5 plus 3. Because 5 plus 3 is 8, it's in brackets, which really mean 2 sets of 5 and 2 sets of 3. And if you look at above, 16 sets of 11 was 4 sets of 11 and 12 sets of 11. And of course, if you want to put numbers on it, 2 8s are, that will give us 16, and that is equal to 2 5s are 10 plus 2 3s are 6. So it makes sense. Another way to look at it would be recognizing that if we have one set of 11, we have it in green. Let's count it across 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have one group of 11, right, which are green balls. And actually we have 2, 3, 4. So we have 4 groups of 11. And how many more groups of 11 will give us 16 of those? That's what the question was asking. So we had 4 groups of 11, which were green, and how many groups of red ones were there? Well, there were 12 more. Let's go on to the last question in the number strand, right, in this first part of the paper. So number 10, arrange the values below in ascending order. And of course, all 10 questions were with 1 mark each. So 50%, 3/4, 0.15. We want it in ascending order. Ascending means moving from smallest value to largest value. So there are different ways to do this. There are at least 3 or 4 ways. One way we can do it is we can look at everything in the same idea of percentages, or all as fractions, or all as decimals, fractions. You can also draw diagrams to represent such. So let's keep it as percentages. 50%, we know that. We have it in green, that's 50%. What is 3/4? 3/4, if we think of 3 quarters or 3 25 cents, that is 75 cents. And 75 cents means 75 out of 100. So I'm converting it to a simple fraction that we're accustomed to, where the denominator is 100. And 0.15 is, if we consider place value, 15 hundredths. So we've put three different colors so we can recognize it easily. So 50%, if we're keeping everything as percentages, that's fine. 50%. 75 out of 100. Out of 100 means percent. So that's 75%. And of course, 15 out of 100 is 15%. So now we can represent this using a number line. And if we think about we're starting at 0 and we're going to a whole, which is 100%, then the middle of that, the benchmark, is 50%. So we know there's a green representation of 15%. So let's bring that 50% down so we know where that falls. We have in purple 75%. 75% will be from 0 to 50 to 100, will be on the right of 50%. So it's somewhere there. And of course in black, we need a black arrow to represent 15%. And that will be between 0 and 50. So now that we know that, we can see our ascending order moving from left to right will be whatever is black, the black arrow, then the green arrow, then the purple arrow. So the black arrow is, let's represent it, 15%, followed by the green arrow, which is 50%, followed by the purple arrow, which is 75%. So we have put it in ascending order. However, when we're looking at that, we want to have the same representations of the numbers that were given in the first line. So our answer should be, what was 15%? 0.15. 50% was still the same. And 75% was 3/4. Number 11, write the time shown on the clock. So we can see from the diagram, it's an analog clock, and we need to write it in a digital format. So let's look at the hour hand. Let's extend it a little bit. We can see that the arrow is almost at the 11, but it has passed the 10. So it lies somewhere between 10 and 11. As such, the hour hand indicates that it's 10 o'clock. And we now need to see how many minutes it is. So if we're looking at the minute hand, that will be the shorthand. Now let's recall that if we cut the clock in half, then at 6, it means that we're at half past or 30 minutes. So therefore at 7 will be 35 minutes. Remember, as we move from one to the other, we're moving 5 minutes. So at 8, which is where our clock is given, it will be at 40 minutes. So it's 10:40. We can also recall that if we cut it across, that at a quarter turn, it was 15. And by the time it was 2/4 was 30, 3/4 was 45. So it was at 9, it was 45. So if it came back down to 8, it reduced by 5 minutes to 40 minutes. Or another way, we could start it up by counting at 1, it's 5, and go through the whole scenario. 2 5s are 10, and we know 3 5s already given, so 4 sets will be 20, 25, and then go up until we get 40. Let's now move on, where we'll be looking at number 12. And in this question, an incomplete calendar is given below. So we have the calendar, which is November, and we have 1 until 26. So the question is asking, what day of the week is the 30th of November? And there are a couple different ways to do this. I just want to remind ourselves that if we recall that each of these lines that's going across is actually a long number line. So 1, 2, 3, 4 actually continues 5, 6, 7 onwards, and so forth. So let's look at the middle one. 12, 13, 14 is really from 10, 11, 12, 13, going on past 18, 19, 20. It's just a number line. And what's happening? We take the number line and we slide it down and move it across 7 spaces, because there are 7 days in a week. So from 12, where we started on Sunday, the next Sunday will be 12 and 7, 19. And we can see the number line continuing to 25 at Saturday, and off the calendar 26, 27, and so forth, which means we can slide the number line down again, and 19 and 7 will give us 26. So we can see the number line there, and we can recognize that on the 30th day, because that is what the question is asking us, what day of the week is the 30th of November? And that would be Thursday. There are other ways you can do it. If we recall, since when we're coming down, we're moving from a Thursday to a Thursday, we're adding 7 because there are 7 days in a week. And of course, 9 and 7 is 16, 16 and 7 is 23, 23 and 7, of course, will be the answer 30. Or we could have worked backwards. We wanted to end up at 30. 30 take away 7 is 23, and 23 lies on a Thursday. Let's now move on to number 13, where it's asking us, Priya drank 5 boxes of the orange juice shown below. So we have the orange juice there, and it indicates that the capacity is 250 ml. So how many liters of orange juice did she drink? So we can bring it up on a number line. There's some students who can easily tell what it is, and there's some who get problems. So let's bring it up like a number line and draw some there, so we can see at 0 there was no juice drunk. Then she drank 1 box, and then 2 and 3 and 4 and 5. So she drank 5 boxes of orange juice, maybe for the week. Right? And what does that tell us? Right? We sort of spread it out, that in the first box was 250 milliliters, and another 250 would be 500 ml, 750, 1000 milliliters, 1250 milliliters, and so forth. She stopped at 5 boxes, so our final answer was 1250 milliliters. Let's look at the question. How many liters? So they don't want the answer in milliliters, they want it in liters. So we can change it. So we have 0, 0.25, 0.5, 0.75, 1 liter is 1000 milliliters. We know the conversion. We've done it so many times in school. A milli means 1000. So 1250 milliliters is the same as 1.25 liters. And that's our answer. Some of us are taught that 4 of these packs of 250 gives us 1 liter. That's fine. And we have a quarter again, so 1.25 liters. Another way that it can be done, 1 box holds 250 ml. So she drank 5 boxes, so 5 times 250 ml, it is 1250 milliliters. And of course, if we're converting from milliliters to something which is a larger value, which is liters, then we need to divide. And we're dividing by 1000. So it means right now, where's the decimal point? At 1250 on the extreme right. And we move it 3 places across, because 3 zeros means we're dividing by 1000. And there we put the decimal point. So our answer is 1.25 milliliters. Let's move on. So we now move on to the next question, which is number 14. And here, the shape below is drawn on a 1 centimeter grid paper. And you can easily see that there. Calculate the perimeter of the shape. What is perimeter? With the idea that it has meter in it, it means it's telling us a distance. And our distance is measured in centimeters because we have centimeter grid paper. And peri means periphery. It means what is around it. So we want to go around the shape and see how many centimeters it gives us. That will tell us our perimeter. Now, when we're doing that, because students are in such a rush when they're writing the exam, they end up mixing up where they started and where they must end. So let's put a little mark at any corner. I'll take here and then move. So let's go downwards. And when we come downwards, let's count it 1, 2, 3, 4, 5, 6. So the red line is 6 long. So it means that our perimeter is 6 centimeters. And we're continuing. We haven't reached back to where we started. Since we went down, we must now move to the right. So we're going to the right. 1, 2, 3, 4, 5, 6 as well. So the distance moved so far is 6 plus 6. And now we have to go upwards. 1, 2, 3, 4. So we're going to add 4 to that. And now that moves down to the right and up. We must now move to the left because we're getting back to the green X. So we're moving 2 centimeters to the left. So let's add 2 to that. And now we must go upwards. When we go upwards to the red line, we'll add 2 more centimeters. So we're adding another 2. And then we're going to the left. 1, 2, 3, 4. As such, we've moved down one direction, to the right 2 directions, up 3 directions, left 4 directions, up 5 directions, left again 6 directions. So it means our perimeter is we're adding 6 distances. We have 6 plus 6 plus 4 plus 2 plus 2 plus 4. 4 and 2 is 6, 2 and 4 is 6. So that's 4 6s are 24 centimeters. So that is the distance to go right around the shape. We could have gone to the right instead of coming down. We could have started at another corner. As long as where you start, you follow along the edge until you're back to the original point. Let's now go to scene in rectangle ABCD shown below. Which side is parallel to AD? So when we speak of parallel, we're speaking of the direction from A to D. And let's draw a little red line. It could be longer than that to show us the general direction of it. And when lines are parallel, it means there's another line to AD where even if they're extended for a long time, they will not meet. If we could look at the line AB, which is going up, AB and AD meet at the corner A. So those two lines are parallel. CD and AD, one is up, one is across, they meet at D. So those aren't parallel. So what is parallel to AD? It will be the line BC. Because if we look at it, both of the lines are heading in the same direction and they're the same distance apart. As such, which side is parallel to AD? That is BC. Draw the line of symmetry on the shape below. And let's recall, what is the line of symmetry? The line of symmetry would be an imaginary line that we can draw on the object so that we can fold the object across it. That way, one side reflects the other. So we have a T shape here, and let's imagine we have a rectangle at the top, which means that we could consider the red line going across to be a line of symmetry. Let's see if that works. If we fold that blue rectangle above the red line and it comes below, will it cover the entire shape? It will complete the rectangle above in the top part of the T, but it won't do the long legs coming down. As such, this cannot be the line of symmetry. So let's consider the left-hand side as an L shape. And if we fold it along this red mirror line or line of symmetry, that on the left-hand side, that L shape will come across to the right side. And it will completely cover the shape. So if we cut this out, we can fold it and we can see that it matches up very nicely. As such, this is the line of symmetry, the red line. Let's now go on, and we're looking at number 17, where the question states, Peter was standing facing south. So we have a diagram there showing us the directions. North is up, to the right is east, down is south, and to the west, that's on the left. So Peter was standing facing south. He turned in a clockwise direction. So that means he moved just like the hands of a clock around the center. And he's moving until he's now facing east. How many quarter turns did Peter make? So if we consider a red arrow showing where Peter started off facing south, and he's making quarter turns. One quarter turn will cause him to face west. And then he has to end up at east. So he has to turn again, and that will give us a second quarter turn. And finally, a third quarter turn will end up at east. So that's where we read the question to make sure we're on the right track. Peter was facing south, and then he turned in a clockwise direction, is now facing east. So how many quarter turns did he make? From south, he went to west, that was one quarter turn. West to north, a second quarter turn. North to east, 3/4 turns. So the answer is 3. Let's now move on to number 18, where these last 3 questions in the paper deals with the statistics. The shoe sizes of 15 students are shown below. So we have sizes 2, 3, 4, 5, and 6. So those are the different shoe sizes for these students. Which shoe size represents the mode? Let's recall MODE, mode. That means the MOST, the most. So when we look at the different shoe sizes, 2, 3, 4, 5, and 6, those 5 sizes, which one of those appears the most in class or is most frequent? So let's check it. Size 2, there's one student who has a size 2 in the class of 15. Size 3, there are 4 of them, so that's more. Size 4, there are 5 students. Size 5, there are 3 students. And size 6, there are 2 students. So which one appears the most? Well, the answer will be 4. So the mode is 4. Some students mix this up and they're saying the answer is 5 because they're counting how many 4s. The mode means which shoe size is the most. And we can clearly see from the green rectangle that 4 appears the most. Let's go on to our penultimate question, or our second to last question on the paper, where it says, Sue Ann scored the runs shown below during a cricket tournament. She scored 24 runs in the first innings, 122 runs in the second innings, no runs in the third innings, and 78 runs in the fourth innings. What was her mean score? So sometimes this is said that this is the average, and that's fine. So what we want to do is be able to represent this visually so students could get a grasp of what we're doing when we're finding the mean. So we'll bring up a bar graph, a little one we could sketch on the side. And in her first innings, she scored 24. In the second innings, 122. In the third innings, there's no bar because she scored no runs. And in the fourth innings, she scored 78. So let's remind ourselves, what do we understand when we're speaking about mean? Mean or average, it's a way of saying that if we redistribute these numbers so that in each innings she scores the same amount, then that value will be the mean. So we can see that she could not score 122 in each innings because she did not score so many runs. She did not score 0 in each innings because she have other numbers to redistribute. So it's somewhere between 0 and 122. So let's take a little average. Let's imagine that in the purple bar in her fourth innings, we're redistributing and assuming that the average is half of that. Let's cut it in half. Half of 78 is 39. So let's redraw that purple. So we get 39 and 39. And why we're doing that? So we can move this across and we can see, okay, in the third and fourth innings, let's assume there were 39 and 39 runs scored each. And what does that mean about the second innings? That we can split it up into 39 below and 83 above. All we're trying to do is redistribute the numbers so we get an even amount. So 39 plus 83 is still 122. We're just keeping it there. And if we're looking at it, the second, third, and fourth columns has at least 39 runs, but the first column is missing some. And she scored 24, so she's missing 15 more. So where can we get this 15 from? From the surplus or the extra in the second column. So if we look at 83, we can split that up. So it will give us 68 and 15. So 68 plus 15 is 83. 83 and 39 is still 122. Still the same number of runs. But we're going to take the 15 and carry it across so that now we have 39 in the first column, 39 in the second, third, and fourth. So the average is at least 39. But if we look in the second column, we have some extras. How much extra do we have? We have 68 extra runs. And we want to redistribute that into each of the columns. How many columns do we have? We have 4 columns because there were 4 innings. So let's divide the 68 into 4. So that's going to give us 17 plus 17 is 34, plus 17 is 51, plus 17 is 68. So we split up the 68 into 4, and now we can take that and share it so that each one of them gets 17 more. The fourth column, the third column, the second column already has 17, and the first column. So now we can see that there's an even amount straight across for each of them, which is 56. And we got 56 by saying 39 plus 17. So that is our mean score, 56. So if she had scored 56 runs in each of the 4 innings, it would be the same as what she did, where she scored 24, which was blue, in the first innings, 122 in the second, 0 in the third, and 78 in the fourth. 56 does the same job. So let's go now. There's another way that teachers normally ask the students to do it, which is find out how many runs she scored in all. So 24 plus 122 plus 0. You don't need to write the 0, it's understood. Plus 78. And that, when we add it up, 8 and 2 is 10. We're adding the 1's values. 10 and 4 is 14. So we have 14 ones. And what do? We take the 4 and place it in the answer. And now we're adding the 10's. We have 1 and 7 is 8 tens, and 2 10, and 2 12. So we have 12 tens. So now we could place the 2 under the tens column. And how many hundreds do we have? 1 and 1 is 2. So she scored 224 runs in her 4 innings. And if we wanted to share it up evenly, then we can do a simple division. 4 divided by 224. Right? So different ways of doing it. 4 into 2 cannot. That's how the teachers normally teach it. It's 4 into 22. And 5 fours are 20. So there's a remainder of 2. And 4 into 24 is 6. So it tells us that her average score is 56. It's important for students to know on the right-hand side what is really happening before they go to do the numbers on the left. Some of my students actually do it on the right side and use that method because it makes more sense to them. Now we come to our final question on this video, which is the end of section 1, number 20, which will also be statistics. The incomplete tally chart below shows the 4 houses to which students belong: Pui, Rose, Hibiscus, and Lily. Complete the tally chart to show the number of students in Lily's house. So we're missing Lily. If you look at the tally chart, we know Pui has 1, 2, 3, 4. So there are 4 of them there in that house. 1, 2, 3 for Rose, with 3 students who are in the Rose house, 1 student in Hibiscus, and 6 students in Lily. So how do we represent that? 1, 2, 3, 4, 5, and 1 more, 6. So this is a way to represent 6. Remember that there's a special way to represent 5. After we hit the 4th one, the 5th one must be diagonal. So 5 and 1 is 6. We have now come to the end of SCA 2020 past paper questions in section 1. In this video, we did all first 20 questions, which were worth 1 mark each. In our previous video, we did the participle questions for section 1 in 2019, and in our next video, we'll be looking at 2021. Don't forget to look at the description down below where we've highlighted the order we suggest you go through these videos in order for you to get a better grasp of this assessment. Okay, goodbye.